All right. Good morning here. First thing I'm gonna say here as I get readjusted is the sound okay? Because I have moved into another room, and so my microphone's set up slightly differently. Hopefully, this is still audible to everyone here, and not too loud or too soft. Um, So if anyone can hear me, say so in the chat. That would be really, really nice of you. Otherwise, I'm going to keep going on as if you can. And that in its own right would be a bit odd. I have a small adjustment problem here to do. Give me a second to fix the screen size here. Can you hear me? Can you hear me? Testing. Excellent, excellent. Thank you, everyone. Thank you. All right. Now let's see this here. Fix the screen size on this. That looks okay. Scroll up here. Sorry, screen has moved. Moved my office into the porch. You might hear some traffic noise in the background, but hopefully the children will be able to deal. All right, so a little bit on the right-hand side there. All right. That fixes that. See, that's what I mean about the traffic noise. Plus, it's been a windy one today, but I think that was the given that it was supposed to be windy. All right, so I hope everyone's doing okay. Haven't been getting a few email questions. I've been trying to respond. I'm adding questions and answers to questions up on YouTube. I will record videos separately for the questions coming back. We're in on the online material. It's chapter 13 in the book. It is chapter, I want to say, 10. We are in the last 3 chapters of the book. Last 3 or 4 chapters of the book. We're covering the materials 8, 9, 10, and 11 in the printed book. 11, 12, 13, 14 on the online book. It is. But there's a little back and forth between the concept of linear equations. I have posted all the worksheets up on Blackboard. If you want to do the worksheets as we did in class, it would be a good practice for everyone to do. And I'm actually going to point out once we kind of work on the graphing stuff here, which worksheets to focus on. I did say we're going to take our time through this, and I like focusing on the graphing portion a little bit more because I like borrowing the ideas that we get from this stuff visually. So that's where we are book material wise. Get jumped into it. If you have any homework, exam, Pearson questions, email them to me. Sorry, I'm going through the mental list of things I wanted to check. Let's see. So we're working our way through. We will. Let's see. We have this week, next week, about 4 weeks to go. Let's see, April to the 20th to the 27th, 3.5 weeks, and we've got 2 chapters that are going to smear over those full weeks, with one more exam in the middle, really to help with points. The big Oh yes, I'm putting all the grades over from Pearson. Um, I normally don't do a grade book visible to students. I kind of have everyone add up their averages. And what I normally did is on the second exam and the third exam, when I handed them back, I would put what my grade book showed the grade on the cover of it. So email me, and I will email me, and I'll email everyone out their current averages on each section. I've tried using the Blackboard bit, and because I didn't set up the gradebook initially, in retrospect, it's a little hard to wedge in. I play with it every weekend in my Mat 143 class. Figure that'll be the place I'll make all my mistakes. And I'm not liking it. So what I'll do, Stacy, is I will email out everyone's grades when I get the exams off of Pearson into my grade book. Generally, what I advise students to do is the grade weights are in the syllabus, and kind of add up the averages for each category and go from there. But email me, though, as a reminder, please. My email box is still my to-do list, and with the way things have been going right now, my to-do lists are fairly long. Longer than the norm. Any other questions? I'm going to be talking about lines for a couple of days. All right. Oh, it's in my pocket. What I want to do here is I want to kind of recap where we're at. We decided we were going to talk about linear equations, which we started out was saying ax plus b equals c. And I said, hey, we can do this really, really neat thing. In fact, I'm going to make these all lowercase just to be consistent. And we said, well, let's make c a variable. And so we switched from this only has one variable, which was x. And we said, well, let's give this two variables. And so I'm going to write out front, we made c into a y. And for better terminologies, we're going to call a m. I don't know how or why m was chosen, but m was, most textbooks are m. And so now we have a two variable. Two variables, x and y. If we don't let y change, it shows us how this makes a line and why this is called linear equations. It gives us every possible answer for c, where in this case, this was, I'll use an example, 3x plus 3 equals 9, then x had to equal 2. It was a solvable thing, because the one variable could only do one thing. And we said, well, let's look at all the possible answers for 3x plus 3. And I'm going to focus on what we're going to call the slope, which job is to chart the rate of change. And we're going to do it in terms of the graphing that we set up. We set up our coordinate grid. Now there is another way this gets written. So linear equations, we get the y equals mx plus b, and the y equals mx plus b, we will see this is called slope intercept form. And it's one people like because we can see what these numbers are. And they will have places on the graph that matter to us. But the way mathematicians sometimes like to talk about it is they'll say it's ax plus by plus c equals 0, where a, b, and c are integers. No fractions. Secretly, all mathematicians hate fractions also. They get rid of them when they can. And this is called standard form or general form. I always forget the name. I think this is general form. If you put C on the right-hand side, it becomes standard form. We'll look at it a little bit, but we're going to spend most of our time looking at this version of the equation. What will happen is these forms will pop up and we'll transfer them into this form. We'll transfer them into this form. And what mathematicians are really, yes, like for graphs. Yes, this makes it really, really nice for graphs and slope-intercept. What mathematicians really are emphasizing on this form, because they write this general form for circles, for parabolas, for hyperbolas, for any set of equations, is notice x is to the first power and y is to the first power. If you write other things like this, x and y won't be to the first power. And that's why they keep this form, because they can sort out all the different types of shapes that they have. But what we do as people is we like seeing these numbers because they tell us how everything's going to graph out. But today I'm really going to want to try to focus on slope and what slope is. Really liking this orange. All right, so let me get my graph here. Whoops. That one, and there is that one. All right, so here is my coordinate graph, my coordinate plane that we're going to use. We have our first quadrant, our second quadrant, our third quadrant, and our fourth quadrant. I'll label the names of the parts of the graph. Blue. So this is the x. Whoops, that came out big. Where did why did that move? Did this move on the screen for you? No, it's in a good place. Okay. This is the x. Uh-oh, I just broke everything. There we go. There is the x-axis, I'll label it that way, and here's the y-axis. And so this records or marks out x values. They're equally spaced. See if I can make my spacings here. This is the part I always slow down on, is drawing graphs, but that's okay. Right. We have some type of tick mark that keeps track of where things are. I'll just put a couple of tick marks in for right now. And then we'll look at these a little bit later. What I want to do is get the little triangles that are hiding in here out. To put a little ruler off to the side of the screen so my tick marks aren't as horrible as they did them freehand. Right, because for some reason the last time all my left sides were more dense than my right sides. Something about being left-handed. We'll blame being left-handed, right? All right, so let me get my volume here. All right. And so these graphs leave us with a position. I can count how far over an x I go. and how far up in y I go. We could keep track of each point as a pair of values. They're x and y values. And so these equations give us possible x and y values. Now, when Descartes did this, what he wanted to look at, and I'm going to take 2 points. I'm going to take, for lack of a better point, 1, 1. And then 1. And that's going to be, let me make sure I have it right, 1, 2, 3, 4. 1, 1, 2, 3, 4, 5. Nope, I want to be there. 1, 2, 3, 4, and there. That's the place I want to be. Sorry about that. But that's what my eraser is for. And so 1, 2, 3, 4, 5. 1, 2, 3, 4. Yeah, 5, 4. And so these are 2 points. These two points lie within the plane, and I will actually connect them by a line if I can here. That way, and going down, not quite that way. And so we have this line that connects these 2 points. There is an equation that would describe that line. And what Descartes was hoping to do by using this plane and these values was he was going to borrow some ideas from geometry, specifically about triangles. And I'm going to sketch in the triangle that we get out of this by dropping down some lines here so that we can see the triangle. And what Descartes was saying was, by making these things at right angles to each other, you're guaranteed to have a right triangle. And geometry had studied a lot of what right triangles do. And we could borrow everything from geometry. But what he noticed, and what became very useful out of the triangles, is that this line, no matter where I go on it, has the same slant. It rises or falls at the same rate no matter where I look at it, and this could be found from some numbers. So I'm going to use some symbols here. I want to say this, oops, it should be red, is the change in my x values. If I go from here to here, the x value changes. And this is the change in my y values. And now, what I'm writing here is the change in y. This is a Greek delta. It looks like a triangle. I always think that the Greeks, their obsession with triangles and this letter probably came hand in hand. When they saw that they were working with triangles and they wanted to pull the letter that looked like a triangle, which is delta. And because of that, in modern mathematics, delta always means change. You'll sometimes hear in movies or whatnot, what's the delta? What's the change? At least I've heard that in movies. What are they talking about? And then I studied some mathematics and it popped out. Well, what we're going to look at here is how much the y value changes from the y value of the first point to the y value of the second point. And that's what these little parts of the triangle spell out, is this change in y and this change in x, or the change in height and the change in length if we give these other names. And so if I want to look at the change, well, down here, I'm going to do my x first. I end at 5. I began at 1. And so my change is 1, 2, 3, 4. Well, that's 5 minus the 1. Our change comes about from the difference between the end point and the starting point for the x values. So I'm going to give a little notation for this. This is my second x value minus my first x value, or the end point and the starting point. And so when we name our points, we'll sometimes number them. So I'll say this is point 1, and this is point 2. So those numbers. Congruently, the same thing happens for y. The change in y is equal to the end point in y, which is 4, minus the starting point, which is 1. And so we know how far this triangle changes based off of the change in height and the change in x. Well, a really neat thing happens here. Let me see if I can. 4. If I do another point here on the triangle, and I'll do this one in blue, and come up 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is at 9, comma 1, 2, 3, 4, 5, 6, 7. And we'll call that point 3. And so we're going to look at what these triangles have in common. So notice this is the same line that makes this hypotenuse of the triangle. No matter what point I put, and I'm going to put a fourth point here, but we're not going to look at the math of the fourth point. It still makes a triangle with this line. And these triangles still have a hypotenuse that slopes the same way. So let's look at point 2 and point 1, and let's look at these changes. So for point 2, the change in y, I'm going to say between points 2 and point 1, is equal to 4 minus 1, because 1 is where it started from, or 3. And the change in x between point 2 and point 1, it ends at 5 and started at 1, so 5 minus 1, which equals 4. All right, so we know how much we change in y between these 2 points. Well, what if I didn't have this point and I was looking at point 3? So I'm going to look at the change in y between points 3 and 1, and the change in x between points 3 and 1. So we're talking about how far I move in the x direction between point 1 and point 3. Well, point 3 ends at 9 and began at 1, so that's 8. Did the 8 show up? Yes, 8 still fits on the screen. All right, that's always good. And then in the y, it ends at 7 and began at 1, and that's 6. So what is this doing for me, right? Why is Jeff plotting these weird points and looking at what could possibly be the similarity? This thing should be the same, but these numbers aren't the same. Now, the thing Descartes was borrowing from, and that a lot of people study in geometry, is that when we'll talk about similar triangles, where this angle is the same and this angle is the same to another triangle. So this triangle and this larger triangle share an angle. And something happens to the sides. And what we want to look at is, let's look at the change in y over the change in x. So for these first points, that's 3 over 4. For this small triangle here, if I look at how much it rises divided by how much it runs, I get 3/4. Well, if I come over here and look at the larger triangle and look at how much it changes, I get 6 over 8, but that can simplify to 3/4. And it's the same. So the triangles that a line create always have the same ratio of height to length, or the base, right? The height to the base ratio is always the same. And this height to base ratio is what we're going to call the slope. Because it's always the same, and it will be different for triangles that have different slopes. If I were to make another triangle, and I'm just going to do a random one here. Let's start over here and go through that point like that. That's not going to have the same change in height over the same change in base. So we'll be able to talk about different lines by looking at this ratio. And that ratio we're going to call slope. And so the equation we get from slope is this. The change in the y over the change in x. All right. I'm going to scroll down and leave my really while I'm erasing the board here, I'll just give a what I ended up doing here. For those of you, so I've moved my laptop and everything onto a standing desk so that I'm not kind of sitting and whispering. And I've got a blackboard over there, but I don't have a camera for it yet. So I've now moved out into the porch and I've got my microphone off to the side scaring me here. And I'm back here on the standing desk. So I can stand, I can move, and come back here and talk. I can go up here and talk. But I'm going to probably adjust some things. So if my handwriting's a little bit out, my apologies. I'm getting used to the new mode of operation. All right, let's get back to this. All right, so here we are. So we have an equation for slope that we've come across with, and we have however my y has changed divided by however my x has changed. And we'll write this mathematically as the last y value minus the first over the last x value minus the first. Whenever you get a pair of points, you can find the slope of the line in between them by subtracting the y's over x. You have to match the points up. Whatever you pick as your second point, the y value for that is first, and the x value for that is first in this equation. Doesn't matter the order you do the points in, but you've got to grab the same points, and I'll show you that in a second. But because y is height, we can say that's the rise, how much it goes up and down. And because x runs left to right, over run. And since I was first taught this, I always remember it as rise over run, rise over run, rise over run. And then I rebuild the equation out of that. The key to this is if my triangle, which I can make out of that line, I'm going to scroll back up here. Right. This line will always make the same type of triangle. It has the same angle here, and that angle is actually what is defining the slope. Angle and slope end up being the same thing. But for us, the Greeks measured that as the change in height over the change in its base. And that ratio of height to base will be the same on the same line. And so we can talk about that as the slope. So I'm using the variable the book uses. My slope is equal to my change up or down over my change left or right. And we can say, hey, this is the rise over the run. All right, so if we look at 2 points, I'm going to do the 2 points mathematically, and then we're going to look at them on a graph. And so I have the points 2, 1, and 4, 2. Actually, I'll start by putting them on the graph. I just need to 2, 1, 4, 2. So I'll just put my graph right below it. Still use green for the graph. I think this is the hardest part about doing this electronically. So I have tools that could do this so fast. And I do think I tend to fly when using these things. But when you have a blackboard, you slow down, right? You give time because you have to write it out. I was just reading a thing from Harvard about why blackboards are better to teach with than PowerPoints or technologies or even whiteboards, is because they force you to slow down. So acute or obtuse, we don't need to worry about the shape of the triangle that comes out of it, Janine. We will learn to take the number that comes out from slope and get a similar concept. The triangle isn't the thing we're going to be talking about as much as how steep that line is. But those ideas of acute and obtuse kind of hide underneath it all. When a line is very, very, very steep, it will have a large angle. When it's very, very shallow, it will have a small angle. And positive and negative will do different things, which we will try to pull out of our numbers. And we're going to use our numbers to make things out of it. But the triangle itself kind of goes away once we make a line. And that triangle, because our grid is at a right angle, it's always a right triangle. So we get all the special things from the right triangle. In fact, most of mathematics, the Pythagorean theorem, a squared plus b squared equals c squared, comes back over and over again. Not because everything's a triangle, but by mapping our numbers in a grid with right angles like this, we get the benefit of using that equation. All right. So I lost my points there for a second in my own blabbering. Trying to tell myself to slow down is what's happening. Because I can draw some things quick on the graph where I would normally be erasing a board and chatting to you. I'm doing it. So let's see here. All right, good. So let's get my points. Sorry, as I put my grids down on my graph. I think this is enough to do the points I need here. The x direction and in the y direction. All right, so my first point is 2, 1. So I come over 2 in the x direction and up 1. So I'll make this first point 1, 2, 1. That's 2, 1. And I'm going to call that point 1. Give it a name. I'm going to say it's 2, 1 because I do my x values first, followed by my y values. And then my second point is 4, 2. Let's see, I think I'll go orange for that. 1, 2, 3, 4, and up 1, 2. there. That's 0.2. And that's 4 comma 2. If you've had geometry, or this might have been said at some point, to make a line, you need 2 points. It's kind of the converse is true also. If you have 2 points, there is a line that connects them. And so once we have 2 points, we can get a line. And one of the things you're going to find as you do anything linear, because there are 2 variables, you need 2 pieces of information. This is a common theme in mathematics. If you add another variable, you add another piece of information you need. And so in this case, there's different pieces of information I can have. I can have 2 points. I can have a slope and a point. I have a slope and an intercept. There's things we're going to define that if we need to know our equation for sure, we need 2 of them. And so for right now, we've got 2 points. And 2 points is enough that we could actually define this line fully. But for right now, I just want to talk about the slope. So I'm drawing it here, and there's some things to note. It has a definite steepness to it. It's a shape that's the same no matter where I look on the line. And it's increasing. If I start at 0 and I go off towards infinity, my y value gets bigger and bigger and bigger. So we're going to say this is increasing. The line is increasing. Well, let's mathematically look at what the slope is from this, just using the numbers. I'll do that. So, just using the numbers from my equation up there. So my m is equal to my change in y over my change in x. My y2 value is 2 minus my y1 value, which is 1, over my x2 value is 4, and my x1 value is 2. So I get 1 over 2, or 1/2. And so this line has a slope of 1/2. All right, I'm actually going to use this graph to put a couple of different slopes on it. There's a very, very nice slope that comes out, and for a lot of things, and we can use it as a comparison, and that's the slope of 1. So I want to put that, I think, in orange. See if I can get this line right. Not a horrible, not the best drawing, but not the worst. All right, so this orange is a slope of 1, and it's not a bad comparison. What a slope of 1 does is, if I looked at this as the fraction, well, 1 is 1 over 1. And that's telling me however far I go up, 1, 2, that's how far I go over, 1, 2. Up 1 over 1, up 1 over 1, up 1 over 1, up 5 over 5. It's equal change in the x and y. The slope of 1/2, I go up 1 over 2, up 1 over 2. So notice smaller, less than 1, smaller slopes are not as steep. The slope tells you how steep it is. If it's a really small number, it's not steep. right? 1/2 is smaller than 1. The line with the slope of 1/2 is not rising as quickly as the slope of 1. And let me show you another slope. I'll show you 2. We'll compare 1/2, 1, and 2. Oops, wrong tool. I need to get my line tool. And this has a slope of 2. So the larger the slope, the steeper the line. The smaller the slope, the shallower the line. So slope becomes a way of having a number that sits in front of our equation that tells me how quickly it's rising. We can also, if we use the term rate of change, say greater rate of change. This changes more quickly. When I move in x, my y value changes more quickly. So this number in the front tells me how quickly the slope is changing. Notice all of these slopes are positive, right? These are all greater than 0. And so these are increasing. I'm going to draw another graph down below. I'm going to use these numbers, but I'm going to use their negatives. So come down here. So slope is really going to be a placeholder for this idea of how quickly things are changing, rate of change. And what we're going to borrow for that idea is the visual idea of climbing, right? I always, when I was teaching in 349 and could see the road out the window, I would always talk about, well, that road has a slope. There's a steepness to it. And I look at the steepness or the slope in equations as kind of the steepnesses of hills. I think that had to do with the fact that I used to be a runner before I became a little large in the tum-tum. All right, so 1, 1, 1/2, and 2. So, okay, let me do this here. The colors are orange, blue, and green. All right. Orange, I'm just going to get my line here. And there are my lines that I want to highlight for you here. Now these lines have slopes, and I actually chose slopes that were similar to the ones up above. I think so this is m equals -1, or the slope is -1. It's descending in y equally when x goes up. So I go down 1 over 1, down 1 over 1, down 1 over 1. That's a slope of -1. Negative slopes decrease. This is a slope of -2. It decreases more quickly. I go down 2 over 1, down 2 over 1, down 2 over 1, down 2 over 1. Notice I'm using the fractional form of this. It's rise over run. and I'm thinking of this as negative 2 over 1. I can go down 2 over 1. Or I could do it backwards. I could go up 2, back 1, up 2, back 1. The negative has me reverse one of them. And then in the blue slope is negative 1/2. And so this gives us some things that we can talk about our slope that help us kind of when we're going to be looking at equations, we're going to see things that pop out of them. This number sitting in front of the equation will have meaning for us. And what it means for us is if the slope, put some rules out here, and I'm put them in math speak because we got to get used to the math speak. If m is greater than 0, that's saying the slope is positive. The line is increasing. And so I'll just draw a line like this. Right? That's what an increasing line does. Moves in that direction. If the slope is less than 0, or we're going to say the slope is negative, the line is decreasing, which means the line goes this way. And so let's look at our two graphs. I'm going to do a quick scroll up and down here. So here, all of these slopes were positive. All of these lines are increasing. This slope was 1. This slope was 1/2. This slope was 2. So positive slopes increase. They start low in y, and as my x value increases, y goes up. And so when I say what I like about graphing is we have a visual clue for what's happening with the numbers. We can say by looking at this one number in front of it, if my equation is getting bigger as my x value gets bigger, or I can talk about it as like a hill, and I am going uphill versus going downhill when I increase my value of x. Right? So all of these are going uphill because our general motion is for x to be better, which is moving from the left to the right. We move in a rightward direction. When the slope is negative, we look at the values as this is decreasing. And we say, hey, our values are getting smaller and smaller with negative slope. And so as negative slope goes through, we can say it's decreasing and we're going downhill. And this downhill value moves us with negative slopes. Sorry, UPS just came up and dropped off the camera I have, so now I can use the blackboard in the future. That's heard in the background. And so we have these two values. If we look at it, negative is down, positive is up. And that's like, I've done a lot of mathematics. I get used to a lot of equations. And as you build these slopes and as you work on these linear forms, you're going to see this number out in front is really going to help you figure out what's happening without having to plug numbers in. If we can get these things where you can look at it and you get an idea of what it's doing, half the battle's done. And that's the idea of using these graphs and focusing on the slope out in front. All right, so if it's positive, it's increasing. If it's negative, it's decreasing. We have the two graphs for it. Well, there is a special slope, which I want to put in a very special color on my overhead, which is what happens when it equals 0. And a slope that equals 0, I want to put it down here. is a constant. It's a straight line. And what this is saying is there is no change to the y value. If we're going to call this the rate of change also, a slope of 0 says my y value is not changing. Right? Let's say if this was negative 8, over here y is still negative 8. And so when a y value doesn't change, we'll say, hey, y equals negative 8. Notice there's no x in there because the slope is 0. So if the slope is positive, the line's increasing. If the slope's negative, it's decreasing. And if the slope is 0, it's this flat line. Now, acute viewers might notice that I'm missing one. And that's what happens. I'll put one more over here. And this blue line up or down, we're going to say is undefined. And this happens because we're trying to divide by 0. Because if it's the change of x and the change of y, so let's take a point here. We'll say this is negative 5 in x and negative 8 in y. Whoops, negative 8 in y. And I'll come up here, and that's negative 5 in x and 0 in y. Well, if I do my change in y, I'm looking at negative 8 minus 0 over negative 5 minus negative 5. Well, anything subtracted from itself is 0. And notice I'm trying to divide by 0. And we can't divide by 0. So vertical lines are undefined. They just don't have a slope. And I can't even write a y equals mx equation for this. This ends up being x equals negative 5. Notice there's no y variable in it. And so these are the main types of slopes that we get out of these things. Is we get, hey, I'm a positive slope. Well, I'm increasing. Hey, I'm a negative slope. Okay, I'm decreasing. Hey, my slope is 0. I'm a flat line. I'm dividing by 0. Well, then you're a vertical line because we can't make you as a y equals mx. You don't have any y value. All you are is an x value. And so that's what these things let us do, is give this description of how things are changing visually. And to do this, you need 2 points. You pick one as your end point and one as your starting point, and your slope is always your rise over run. You have homework where you're going to play with these equations. I want to emphasize what the equations mean, but I also want to look at an idea of how slope and rate of change come together. I'm going to pop over here for a second. Words. Yeah, words. I'm going to read this, and I want to show you how we can get this to get some information out of it. So it says, suppose that a family on vacation is driving out of town at a constant speed. And I'm going to give some clues here. A constant speed means rate of change. And rate of change is definitely going to be related to slope. Right? And then at 2 o'clock they have traveled 110 miles. By 6 o'clock they have traveled 330 miles. So what I'm going to do here, so I'm going to switch back to the graph, and I'm just going to look at the time and the distance. Well, the time and the distance look like two variables to me. So I'm going to make a little grid here. And down along this side here. 4, 5, 6, 7, 8. And so this will be 2 o'clock, 3 o'clock, 4 o'clock, 5 o'clock, 6 o'clock, 7 o'clock, 8 o'clock. They're traveling through. And then what was the other thing they did? They traveled 110 miles and 330 miles. So let's see. How do I want to count? I'll count. We'll say this is 100. This is. So we'll count by 20s. So this is 340. I'm just trying to put a grid here to see how these come to align. So I'm starting at 100 here and I'm going up to 340. But what I want to do, I'm going to come back to here, right, as I lose you guys for a second, is I want to think of this as a y value and these as x values. I have two different variables I'm keeping track of, but I want to think of a y value and an x value. A y value and an x value. And so I have my time as my y value and my distance as an x or a y. Time as an x, distance as a y. Time as an x, distance as a y. So that's 2, 110. And up here, 3, 330. Now, if we think of slope as rate of change, and remember, rates could have units, then my change in y is this minus this. Whoops, I am 330 minus 110. Right, I said this minus this. Right, my change in y over my change in x, which is 3 minus 2. And so, or whoops, not 3 minus 2. This is 8. I wrote an 8, but it looked like a 3. What is wrong with me? There we go. So I have mapped my two variables onto a grid. I don't care if they're time, if they're distance or position, if they're the number of jelly beans in a jar. I can take my variables, and because they're two different things, this is time and this is distance, they are perpendicular to each other. I can keep adding hours and it doesn't change what I do with the distance. Now if I'm moving at a constant rate, I have two endpoints. So I have 330 miles and 110 miles. If I subtract those two, I get 220, and 8 minus 2 is 6. 6. Calculator. 220. 6. Is I get 36.67. So there is a rate of change. Okay, so what does this number mean? Remember when we did rates, units mattered. This unit is miles. This unit is hours. This is miles over hours. So this becomes 36.67 miles per hour. The points that we use in these variables tell us the rate of change, tell us the speed. What's going to be nice is we can get an equation of a line out of this, which is what we're going to do next class. So we're going to turn these slopes and these points into equations of lines that will be able to tell us where they are if we know the time. So these things start doing something for us that we haven't done before. We start making equations that don't just solve the problem we have. They solve any possible problem where a car is traveling at 36.67 miles per hour. They give us multiple answers in a few steps versus one answer. And then that could be useful if you're this family traveling and you need to go, to 3 different places and you need to figure out what those times are. Or you have to stop every so often to make sure grandma gets her medication in the back. You know how far those stops are distance-wise along the route. The creating these things linearly give us something that we can solve for anywhere along that line. I can look at how far will we be at 2, 3, 4, 5, 6. How far are you at 6.21 hours? Right? It exists on that line. There's an answer. And so these things set up information. They also put the information in the right place to do the word problem. So I'm going to go back to the words here. And if I have a graph, I don't have to worry about making an equation. I don't have to go, okay, this is a time problem with distance, and I need to turn this into a velocity, so v equals d over t, and memorize an equation. I have 2 variables. I'm putting the points I have on a graph. I'm labeling them 2 different things. And in doing that, in putting those things on a graph, the slope becomes an answer to what I can do with those 2 variables. And in this case, the slope is the speed. I'm going to leave it on that. We've made it to the, we've been here for an hour. That's about how far I like to lecture on the video thing. What I'm going to recommend here is on Blackboard, there is the worksheets for Chapter 13. I recommend that you print those out if you can, or at least bring them up on the computer and start working them out to get a practice for these. That's going to get us to the next 3 classes, right? We're going to do, next 2 classes. This was the first one. Well, we're going to spend 4 classes altogether on Chapter 13. We spent the last one on introducing the coordinate plane. Today we just talked about slope. And then Wednesday, we're going to talk about equations of lines, and Monday we're going to talk about equations of lines again and how they work graphically. There's a lot of nuance in this, and we're going to go back and forth with it. What I will do is I will also email out the PDF for the worksheet for this section. But it is Chapter 13 on the online. It is up on Blackboard in the course content. I have all the worksheets out. But I really want you to understand the power of this. It means that you don't have to memorize, what do I do when I get this type of problem? You look at your 2 variables and you go, I'm going to make one my x-axis, one my y-axis, and my slope is the rate of change between those things. And a lot of times, the rate of change has a meaning. All right. I'm going to turn off the audio here. I'll tidy up some things. If you have any questions, shout them. Otherwise, have a good day. Email me if you need anything.